Imagine you're a mathematician in Victorian England. You sit down every day with pen and paper calculating numbers for ships, for banks, for engineers building bridges. Hour after hour, and every few pages you make a tiny mistake, one wrong digit, and that mistake gets printed in the table that ships use to navigate. And ships sink. Charles Babbage lived with that problem, and somewhere around 1830 he had an idea. What if a machine did the math instead? No tiredness, no distractions, no errors. He never finished building it. The technology of his time wasn't good enough, but his colleague Ada Lovelace understood something even deeper. She wrote the first program for a machine that didn't exist yet. And she asked a question that still has no clear answer. Can a machine do more than calculate? Can it think? That question started everything. Fast forward 100 years, World War II. A quiet Englishman named Alan Turing is cracking Nazi codes with one of his first real computing machines. After the war, he published a paper and asked, how would we even know if a machine was thinking? He proposed a test. If you can't tell whether you are talking to a human or a machine, does it matter? That's still one of the most unsettling questions in the field. In 1943, two American scientists, McCulloch and Pitts, looked at how neurons in the brain sent electrical signals and said, we could probably build something like that with logic gates, a mathematical neuron, not biologically, but close enough to be interesting. All the ingredients were collecting. Someone just had to mix them together. That someone was a group of researchers who gathered at Dartmouth College in 1956. John McCarthy, Marvin Minsky, Claude Shannon. They spent a summer working on what McCarthy called artificial intelligence, a name he coined right there. The field had a birthday. The optimism in those early years was almost embarrassing in hindsight. Programs appeared that could prove math theorems. One system called GPS, General Problem Solver, tried to capture how humans reason. A checkers program taught itself to play and started beating humans. In 1965, one of the most respected AI scientists in the world predicted that within 20 years, machines would be able to do any human job, but he was off by about 50 years. And here's what they didn't understand yet. The real world is messy. A program that worked beautifully in a neat, well-defined problem fell apart the moment you ask it something slightly different. The computing power needed to handle real complexity. That was enormous. Way beyond what any machine of that era could provide. And nobody had solved the question of how to give a machine actual knowledge about the world, not just rules for specific games. The money dried up. The research slowed. AI entered what researchers called the first AI winter. A period when the promises had been made, the promises hadn't been kept, and the whole field quietly retreated. It thawed briefly in the 80s. Companies built expert systems. Programs scrammed with the knowledge of specialists. A medical system called MYCAN could diagnose blood infections as accurately as some doctors. IBM's systems configured computer orders for customers and saved companies millions. There was real money in AI for a few years. Then the second winter came. These systems were expensive, fragile and couldn't learn anything new on their own. Every piece of knowledge had to be typed in by hand. When something unexpected came up, they broke. The market collapsed. But somewhere in the cold, something was quietly growing. The idea of neural networks, machines loosely modeled on the human brain, had been around since the 1940s. The concept? Instead of programming rules, you build a system with many layers of connected nodes, exposed it to millions of examples, and let it figure out patterns on its own. Like a child learning to recognize a dog, not by reading a definition, but by seeing 10,000s of dogs. The problem was that nobody had enough data, and nobody had enough computing power to train these systems at the scale they needed. Both of those things arrived in the 2000s and 2010s. The internet had produced oceans of data, and a surprising source of computing power had appeared. Graphics chips, originally built for video games, and GPUs turned out to be incredibly good at the kind of parallel math that neural networks needed. In 2012, a neural network called AlexNet entered an image recognition competition and didn't just win. It destroyed the competition by a margin that stunned everyone watching. The field shifted almost overnight. Deep learning had arrived. What followed was fast. Google's DeepMind built a system called AlphaGo that beat the world champion at the ancient board game Go, a game so complex that many experts had said computers would never crack it. AlphaZero then taught itself chess and Go from scratch, with no human knowledge fed in, just the rules of the game. Within hours, it was playing at a level no human had ever reached. Then came 2017. A Google research team published a paper called "Attention is All You Need." It described a new architecture called the transformer. You don't need to understand the details, just know that it changed everything. The transformer made it possible to train language models on an enormous amount of text and learned patterns across very long passages. In 2020, a system called GPT-3 appeared that could write coherently, translate languages, answer questions, and hold a conversation that felt at times disturbingly real. For the first time, millions of people outside research labs started asking, wait, is this actually something? Then, in November 2022, ChatGPT was launched. 100 million users in 2 months. That number had never been reached that quickly by any other product in history. Whatever AI had been before, something in the background, something for specialists, it was now something anyone could try. Which brings us to the last 18 months. By early 2026, the leading AI models, ChatGPT 5.2 from OpenAI, Gemini 3 Pro from Google, Claude Opus 4.5 from Anthropic, had become what practitioners called a top stack. All three capable enough that the differences between them were almost about price and use case, not raw power. In April 2026, OpenAI released GPT 5.5 with a context window of 1 million tokens. That's roughly the length of 10 novels that the model can hold in its working memory at once. These are reasoning models now, not just answering questions, but working through complex problems over extended sessions, like a colleague who actually reads the whole document before commenting. But the more interesting development isn't any single model. It's what's being built on top of them. AI agents, systems that don't just respond to questions, but plan, take steps, and complete tasks. Move from research projects to real products. AI that can consolidate your open browser tabs, draft and send emails, book appointments, manage workflows. Microsoft called 2026 the year AI moved from instrument to partner. According to the OECD, 20% of companies in their member countries were using AI by 2025. That's up from under 9% just 2 years earlier. Fast by any measure. And then there is a part of the story that surprises people most: robots. 2025 was the year robots and robotics crossed from impressive demos to serious commercial use. Amazon surpassed 1 million deployed robots in its logistic warehouses. Humanoid robots, machines that build to walk on 2 legs and work in spaces designed for humans, moved from YouTube highlight reels to actual factory floors. Autonomous vehicles made the same jump. Robotaxis are running in Phoenix, Las Vegas, San Francisco, Shenzhen. In 2026, that footprint is expanding into Europe, the Middle East, and Asia. Not test programs anymore, regular transport options. The technology making all of this possible has a name: Vision Language Action Models. Systems that can understand spoken instructions, see what they are looking at, and plan how to move through a real environment. A robot that you can actually talk to. So, from Ada Lovelace writing the first algorithm for a machine that didn't exist yet, to AI systems that can hold 1 million words in memory, reason through complex problems, and walk across the factory floor on their own. Almost 200 years, 2 winters, dozens of false starts. And in the last 3 years, a pace of change that has left most organizations, governments, and individuals simply trying to keep up. The question that comes after the history is the practical one. Now that we have the technology and it is accelerating, what do you actually do with it? That's the question worth spending time on.